In the previous video in the quantum mechanics playlist, I constructed a Lagrangian that describes two coupled and driven anharmonic oscillators. In this video, I'm going to continue analyzing that system. Let's do a quick recap of the stuff that we found in the previous video. Let's begin with the Lagrangian. So this top red line over here is the Lagrangian. The Lagrangian depends on coordinates and time derivatives of the coordinates, which we can think of as velocities. There is also an explicit time dependence. Both these quantities are dynamical quantities. They depend on time. So there is an implicit time dependence through these two quantities, but there is also an explicit time dependence over here. And that explicit time dependence originates from V1 and V2. Those are time-dependent driving voltages. And we can model them as cosinusoidal functions, or even as more complicated functions. But the important point is that these are time-dependent functions, V1 and V2, and they are voltages. So that is where the explicit time dependence comes from. These capital Phis are fluxes, and these capital Phi dots are time derivatives of the flux. We can think of them as coordinates and velocities, as an analogy to mechanical systems. So this system is an electrical system, but the mathematical relationships are very, very similar to mechanical systems. That's why I keep calling this position and velocity. So this k over here is shorthand notation. It is an index, and in this case, k goes for values 1 and 2. So we have two coordinates and two velocities. So wherever you see k, just think of k equals 1 and k equals 2. Those are the two possible options. So this is just shorthand notation because we have more than one coordinate. So let's have a look at some of the terms in this Lagrangian. All of the terms that I have written out over here, they are capacitive terms. And capacitive terms go in the kinetic energy because they depend on the velocities. They depend on the time derivatives of the fluxes. We see Phi1 and Phi2 over here. So here we just have a dependence on Phi1 dot, and here we have a dependence on Phi2 dot. This is a mixed term, and the coefficient of the mixed term comes from the coupling capacitance. That's coupling between the two anharmonic oscillators. These two mixed terms come from capacitive coupling to external voltage sources. So this is external driving on the first oscillator and external driving on the second oscillator. In the previous video, there was also another term. There was a collection of terms that had V1 squared and V2 squared. But those terms didn't have any of the Phis or the Phi dots. So there was no dependence on the coordinates or derivatives of the coordinate. So what does that mean? That means we can neglect those terms because we're only interested in derivatives of the Lagrangian. So all of these terms that I've explicitly written out here, they are kinetic energy terms. Implicitly, we also have the potential energy terms over here. So the Lagrangian is defined as the kinetic energy minus the potential energy. And the potential energy only depends on the coordinate. So over here, we have inductive terms. So all of the inductive energy contributions, they are in this term over here. But we're not going to be focusing on the potential energy in this video. We're just going to be focusing on the kinetic energy. So let's have a look at what we can get from these kinetic energy terms. We can take partial derivatives with respect to Phi1 dot and Phi2 dot. And that's actually going to give us the canonically conjugate momenta. And the canonically conjugate momenta for this physical system are charges. That's Q1 and Q2. So let's have a look at these blue expressions over here. What are the terms in these blue expressions? So this first row comes from taking the partial derivative of the Lagrangian with respect to Phi1 dot. You can see this term, and this term, they contribute to these three terms. And analogously, if we take the partial derivative of the Lagrangian with respect to Phi2 dot, we get these three terms. They come from this term, and this term. So the first term over here is what you would expect if you had independent oscillators. If we switched off coupling between the oscillators, that would get rid of this term over here. This C12 would go to 0, and this C12 would go to 0. So these terms would disappear. And if we switched driving off on both of the oscillators, that would get rid of these terms. So if we switch driving and coupling off, then we just get this. And this is exactly what we've seen in previous videos when we're describing LC circuits or transmods. When we describe transmods and LC circuits, if they're just independent, just by themselves, this is the relationship that you get between the charge and this velocity. You can think of it as a velocity, phi dot. This is just like the momentum is equal to the mass times the velocity in classical mechanics or Newtonian mechanics. So that's the relationship between momentum and velocity. There's just a scalar factor of the mass. So capacitance is the electrical analog of mass in this case. It's not an exact analogy because you have different capacitances appearing all over the place, but you can make a rough analogy between the role of capacitance in these equations and the role of masses in Newtonian mechanics for mechanical systems. So we've seen that if we turn off driving, that gets rid of these terms. If we turn off coupling, that gets rid of these terms. And that just leaves the relationships that you would find for two independent anharmonic oscillators. It's a similar relationship for harmonic oscillators, which are just a special case. That's if the energy levels are evenly spaced for harmonic oscillators when we translate into quantum mechanics. So we have these canonically conjugate charges, or momenta. That's these blue equations over here. And we derived them from the Lagrangian. And you can see that the potential energy, the inductor terms, they played no role in this derivation over here. That's because the potential energy does not depend on the phi dots. It only depends on the phi's. Now what I want you to look at is this matrix equation over here. We can translate these two equations into a matrix equation. So all I've done to go from this step to this step is I have added these driving terms to both sides. And then I've just turned these coefficients into a matrix. So this matrix over here takes into account all four of these coefficients. And you can see if you perform this matrix multiplication, you get this over here. So this is a column vector. It has two entries. And this over here, this is also a column vector with two entries. So we're just translating two equations into these column vectors. And then we can see that we can pull out these coefficients in a 2x2 matrix. So this is a 2x2 matrix, and this is a column vector. So this is very convenient, because now what we can do is we can take the inverse of this matrix, and we can rewrite these equations where these phi dots are written in terms of the q's. So let's see how we would do that. The first step is to define some useful quantities. So in the previous video, I defined C1 and C2. That's the sum of all of these capacitances. And this really condenses the form of the Lagrangian and the form of these equations over here, because this sum of three capacitances appears very often in these expressions. And this absolute value of C actually denotes the determinant of this matrix. So this matrix that contains all the capacitances, these coefficients, it is summarized by the determinant. So when we take the determinant, we need to take the product of C1 and C2 and subtract off the product of these two terms over here. So we're going to have minus times minus, and then we have another minus, and that's going to give us this combination. So this is the determinant of this matrix. And if we take C to be this transformation matrix, the capacitance matrix, what we can observe is that C times its inverse is going to give the identity. And we can also do it the other way around. Because this is just a 2x2 matrix, we can swap the order of the inverse and this matrix. And that's just going to give us the identity. And this capital I denotes the 2x2 identity matrix. And if you were to perform matrix multiplication of this matrix with its inverse matrix, that would give you the identity. So there would be ones on the diagonal and zeros on the off diagonal. And another more concise way of writing this matrix equation is this little blue equation over here. So Q bar is this column vector, and phi dot bar, that's this column vector over here. And C is just this matrix. So the letter C just denotes a 2x2 matrix. And when we put these absolute value signs around C, that is the determinant. And what you can see is we can just take the inverse C and multiply that on both sides, and that gives us this equation over here. So if we want to isolate this phi dot column vector, all we have to do is find the inverse matrix and multiply it by this Q vector over here. And that is what I've done over here. So you can see now I've written this in the inverse way. So now we have the inverse matrix. So as an exercise, what you can do is you can multiply this matrix by this matrix, and you will find that you get the identity matrix. And try doing it in both orders. Try multiplying this by this, and then this by this. And don't forget to divide by the determinant. So you have to divide by the determinant when you take the inverse of a 2 by 2 matrix. And you can see the procedure is, all you have to do is swap the diagonal entries. So C2 goes up here, and C1 goes down there. And you have to negate the off-diagonal entries. So over here now we have plus signs where there were minus signs. And this matrix equation can then be multiplied out. We have this 2 by 2 matrix and this column vector. We can perform matrix multiplication, and that gives us these expressions. And I have color-coded these entries of the column vector. And these relationships over here involve the determinant of C, of that matrix C. And what we've done over here is we have expressed the velocities in terms of the momenta. So now in later equations, when we have these phi dots occurring, and we want to express everything in terms of the momenta, that allows us to just use this equation. We can just substitute these expressions into that equation, and then perform all the tedious algebra, collect all the terms, and that will give us an expression that only depends on the momenta. And why would that be useful? In Lagrangian mechanics, we like to express everything in terms of phi's and phi dots. Lagrangian mechanics likes to deal with velocities. But Hamiltonian mechanics prefers to deal with momenta. So when we have a Hamiltonian written in terms of phi's and phi dots, what we would like to see is something written in terms of phi's and q's. And these expressions over here enable us to derive those expressions. So that is the desired Hamiltonian. And then after we have the Hamiltonian written in terms of phi's and q's, we can translate it into quantum mechanics. But first, we need to find the Hamiltonian. And the procedure for finding the Hamiltonian, if you have the Lagrangian, is called the Legendre Transform. So let's write down the Legendre Transform. The Hamiltonian, if we're expressing it in terms of the phi k's and the phi k dots, is going to have the following form. So I'm also including this explicit time dependence, because we have an explicit time dependence over here. And we will later translate this into the language of q's. We will write it in terms of the momenta and not the velocities. But let's write down the Legendre transform first. So what we need to do is take the sum over k equals 1 and 2. So there's the two possible values for this index k. And we need to take the sum of all of the canonically conjugate charges. So those are the momenta. We'll put a little index k. We have to take the product of this with all of the phi k dots. So these are analogous to the mechanical momenta and the mechanical velocities. So we have momenta and velocities. And then when we have this big product and this big sum, we have to subtract off the Lagrangian. And the Lagrangian depends on phi k and phi k dot, and it also has an explicit time dependence. But we can split this Lagrangian into a kinetic energy and a potential energy. So what I'm going to do is I'm going to split this up into its components, and I'll split this Lagrangian up into its smaller components. So that's going to look like this. We're going to have Q1 phi 1 dot plus Q2 phi 2 dot. And then we have to subtract the kinetic energy, which depends on phi k dot, and there's also an explicit time dependence coming from V1 and V2. So when I write k as a function of the phi k dots, this is condensed notation for all of these capacitive terms. And now, because we're taking the minus of the Lagrangian, we have to have a plus over here for the potential energy. and the potential energy only depends on the coordinates. In this case, there is no explicit time dependence over here for our model of the system. But in general, you could put a explicit time dependence in here. But just for our system, there is no t. There is an implicit time dependence because the coordinates do depend on time. So this is the Legendre transform. We have the Hamiltonian expressed in terms of the coordinates and the velocities, and that is equal to this combination. So this is the Legendre transform, which takes the Lagrangian and transforms it into the language of Hamiltonian mechanics. So let's find this sum over here. And this sum is equivalent to this. We have all the information we need. We have the q's and we have the phi dots. So first, we're just going to deal with the phi dots. And then in later videos, we're going to translate this into the language of q's. So underneath, what I'm going to write is the following. We're going to have q1 multiplied by phi1 dot. So we need to take this q1 and multiply each of the terms by phi1 dot. That's going to give us c1 phi1 dot squared. We have another factor of phi1 dot over here. Then we're going to have minus c12 phi1 dot phi2 dot. So there's already a phi2 dot. I'm just introducing another phi1 dot. And then we're going to have minus cv1 v1 phi1 dot. So this takes account of this final term over here. And now let's do a similar procedure for q2 times phi2 dot. So we're going to have plus c2 phi2 dot squared. So we have an extra factor of phi2 dot. And then we have the mixed term c12 phi1 dot phi2 dot. Then we have an extra factor of phi2 dot appearing over here. That's minus cv2 v2. And we have phi2 dot. And you can see that some of these terms are looking very familiar to the terms that we have in the Lagrangian. So we're going to have to group a lot of these terms together to see it more clearly. But we do see that mixed term emerging over here. That's the same mixed term that we see here. And we also see those quadratic dependences. And then we see these remaining driving terms. So let's write down the rest of this expression. So we also have minus the Lagrangian as a function of the phis and the phi dots. And we have an explicit time dependence as well. So now what I want to do is I want to write this out in a more suggestive form. So that's going to equal, we can group a lot of these terms together. Let's write this as 2 times c1 on 2 phi1 dot squared plus c2 on 2 phi2 dot squared. And we have 2 copies of this mixed term. That's this mixed term and this mixed term over here. So we're going to have minus c12 phi1 dot phi2 dot. And I'll close the brackets over here. You can see that the 2's cancel with the halves, and that gives us this term, and I've just collected 2 copies of the mixed term. And then finally we have the driving terms. So I'll write the driving terms over here. We have c v1 v1 phi1 dot minus c v2 v2 phi2 dot. And I'll split this Lagrangian up into 2 parts. We're going to have the kinetic energy part, which just depends on the time derivatives of the fluxes, and there's an explicit dependence on time. And we have plus the potential energy, which only depends on the fluxes. So this is the Legendre transform. Can you see some things that we can cancel? So this k over here is equivalent to all of these terms. So what we have to do is take these terms and then subtract off all of these terms. Can you see that these first 3 terms are identical to what is written in the brackets? We have 2 copies of everything in the brackets minus these terms over here. So if we subtract these terms from this over here, we're just going to have 1 copy of what's in the brackets. And also notice that these terms, these 2 terms over here, the driving terms, they are identical to the driving terms over here. So if we subtract this k from this, these terms are going to cancel. So those driving terms are going to disappear. And that's going to give us the following. I'll write this underneath. We're going to have C1 on 2 phi 1 dot squared plus C2 on 2 phi 2 dot squared minus C1 2, and we have that mixed term which has phi 1 dot and phi 2 dot, and these terms have disappeared. They've cancelled with the other terms in the kinetic energy, and then we just have plus v, and this is a function of the coordinates. And this is the Hamiltonian. If we had kept that extra term in the kinetic energy that depends on v1 and v2, well, then we would have just carried that along. It would have gone along for the ride in the Legendre transform, and it would show up as an additive constant over here in the Hamiltonian. But that's why I chose to neglect it, because it is just an additive constant. It does have a time dependence, but it is still an additive constant which does not depend on any of the coordinates or derivatives of the coordinates. So what we have over here is the Hamiltonian. But the Hamiltonian is written in terms of phi's and phi dots. So this is useful. We have a useful Hamiltonian which does describe the coupling, but where have the driving terms disappeared to? We have driving in this system, but they don't show up in this Hamiltonian. Explicitly, we can't see them, but implicitly, they are still there. There are still driving terms present in this Hamiltonian. And we will see that those driving terms will emerge when we substitute these expressions into here. So all you have to do, this could be an exercise, this over here, you can substitute all of the phi dots and replace them with q's, so these big expressions. And when you have that, when you square these expressions and multiply them together, and then collect all the like terms, what you will find is a very interesting expression. There will be terms that describe independent anharmonic oscillators, and there will also be coupling terms and driving terms. We will see terms that are analogous to all of these combinations over here. But instead of phi dots, we'll be dealing with q's. So I'll write this explicitly down here. So what we're going to do is we're going to take the Hamiltonian written in terms of the coordinates and the velocities, and we're going to rewrite that, re-express it. It'll still be the same Hamiltonian, just expressed in terms of different quantities. We're going to express that in terms of the coordinates and the momenta. And there will still be an explicit time dependence. And then after we do that, we can redefine these quantities and make them dimensionless quantities. So we can further change this Hamiltonian and re-express it in terms of lowercase phi's, and instead of capital Q's, we'll have lowercase n's. And we'll define what these quantities are. So this phi over here is actually a condensed notation for the combination 2 pi phi naught over, actually this should be phi k over here, phi k over phi naught. And phi naught is the flux quantum. So I'll write that flux quantum over here. The flux quantum is Planck's constant over twice the charge of the electron. That's what this phi naught is. And this is defined to give us a dimensionless parameter which neatly goes into cosines. So we can put this into cosines. And those terms appear in this potential energy. So I haven't explicitly written them here, but in the previous video, you can find those terms. And we'll be dealing with these terms in later videos as well. So I've written what these lowercase phi's are, but what about the n's? Let's write down these n's. Well, the n's, n sub k, those are equal to the q's divided by twice the charge of the electron. And you can see that these coefficients, these little constants, keep appearing in a lot of the equations. So we have 2e appearing here and 2e appearing there. That's because when you're dealing with superconducting devices, the electrons tend to come in pairs, and those pairs are called Cooper pairs. So that is the physical reasoning as to why we have defined these quantities. So this has units of charge, and 2e, that has units of charge, so this turns into a dimensionless quantity. And phi, capital Phi over here, has units of flux, and we're dividing by something that also has units of flux. You can see that the units of flux are the same as the units of Planck's constant divided by the units of charge. So this gives us a dimensionless quantity as well. And what we can do is, when it's in this form or this form, we can translate this into quantum mechanics. And I'll write that underneath here. What we can do is we can promote these guys into operators. So that's going to give us a Hamiltonian operator. I'll put a little hat on top to distinguish it and make it an operator. And it's going to depend on the operators phi k and n k. And we also have an explicit time dependence. Time is not an operator over here. Time is just a label for a lot of the dynamical quantities that we see. So that is actually a deep question, whether time could be treated like position. But we're not going to go into that in this video. So the first quantization, or the canonical quantization procedure, takes these quantities, these dynamical quantities, and it promotes them into operators. So that's what we're going to do. So I'll do a quick summary as to what we've done. We've started with the Lagrangian. We've analyzed some of the quantities that we derived from the Lagrangian. And then we used the Lagrangian to construct the Hamiltonian by performing the Legendre Transform. So this is the Legendre Transform, which takes the Lagrangian to the Hamiltonian. But this Hamiltonian is written in terms of the coordinates and time derivatives of the coordinates. So what we're going to need to do in later videos is rework this Hamiltonian by substituting these expressions in here, and then that's going to give us a Hamiltonian that depends on the phi's and the q's. So with an analogy to mechanical systems, you would have positions and momenta. And then what we can do is we can define dimensionless quantities, and those are the lowercase phi and the lowercase n. And everywhere over here where I've written k, k is just an index, it is a placeholder, and you can substitute the values 1 and 2, because we have two coordinates for this physical system. That's capital Phi 1 and capital Phi 2. And then the final step is canonical quantization. So this is an essential step in circuit quantum electrodynamics. What we're doing is we're taking a classical description of an electrical circuit and translating it into the language of quantum mechanics using operators and Hilbert spaces. So this is what we'll see in the next few videos in the quantum mechanics playlist. And you can find those videos if you click over here.